The American industrialist Henry Ford said, "Chop your own wood and it will warm you twice." And that is the exact form of thinking that I have adapted for my project. In gyms across the world, across North America, people go, they work out, and where does that energy go? It's wasted as heat. Some of the machines they use even take power from the grid in order to run. And so my project looks at whether the community college could benefit from machines that would take that kinetic energy that you're putting out and turn it into electrical energy. So I'd like to thank you all for coming. Thank you to the members of staff that aren't directly related to Chemtech. Thank you for the fellow students that have come out to show your support, and I hope that you're both entertained and educated this morning. So I will start off logically with my thesis. I will give an overview of the scope of my project and give you a little bit of context, what we're talking about. I want to talk about my approach this morning, not only how the energy is used, but also how we get it. I will wrap up with conclusions based on both the method of energy use and attainment, and my recommendations. So, what benefits would MBCC get from exercise machines that convert kinetic energy to electrical energy? And in my report, I look exclusively at the financial benefit. The college is, after all, business. They want to know if it will pay off. So, unfortunately, I did not design any machines. Everything that I'm going to present today is readily available for purchase. You can find it on the internet, from suppliers' websites, and there's even one I found from Amazon. But I did not compare a comprehensive list of all the machines on the market, just a select few. And even this morning, for the sake of time, I will only be taking you through some of the ones that I looked at. The prices for the machines are just that, just the price of the machine. Shipping is not included, installation, extra hookups, those aren't included either. And this provides us with a kind of apples to apples means of comparison. Some of my approaches are a bit simplified with regards to my calculations, and I will explain my assumptions and why I've made them. So let's go on a tour of the spin studio where the bikes are located. It used to be a study, according to the original plans, that the folks in the maintenance department let us look at. So, as you can see here, it's not a large room. There's one bike at the front. There's a single exterior wall with 6 windows. And then back here there are 8 other bikes. There are 2 different types of bikes. They all work on the same principle, but there are 2 different models. And the other room is not dedicated solely to exercise equipment, to exercise machines, but also to weights and various implementations with which to torture yourself in a weight manner. And so you can see that on this side of the room, many of the things are dedicated to weight training, and over here closer to the wall, you have the treadmills, the elliptical, and the rowing machine. So now you know what we're talking about. We're going to talk about the first idea for energy use, and that was one suggested to me by Doug Scott. He said, is it worthwhile if we heat water and store the energy that way? And so I looked at how much water would be needed for a shower. I took the time limit of 5 minutes, which isn't unreasonable, I don't think. and you'd need 47.3 liters of water. I went to the showers, and Kevin Dorian from Chemtech lent me a beaker and a thermometer, and I measured both the flow rate and the temperature of the water, both on cold and on hot, so I could kind of have an idea of how much the water needs to be heated. And it needs to go from 20 degrees Celsius, which admittedly is a bit generous, but it's a moot point here in a minute. And you need 2,100 kilojoules to heat it. And the time to generate that much energy at 300 watts, which is quite a pace. That's you got to be almost Clara Hughes to generate that much energy. You have to be going for 2 hours. And then the other issue is space. If we have water heaters, we've got to put them somewhere. Right now, the water comes from the boiler, so the boilers are already in place. You don't need additional infrastructure. So I was allowed pictures of the renovation plans, and I did. Oh, sorry. I made a scale circle for the size of the top of a hot water heater, and the blue lines off of it show how it would be hooked into the existing water mains. And as you can see, there's not a whole lot of space for them. Awkwardly, they have to be put almost inside the shower to be close enough to use. The next thing I looked at was heating and ventilation, how to heat the room and cool the room. So first off, we'll start with heating the room. If I told you that you're in a square room and it has a single exterior wall, what would you infer about the other 3 walls? Precisely, Mike, they're interior walls. And that's exactly how these rooms are heated. I checked out the thermostat, and it's set at around 14 degrees Celsius. And that allows a nice cool atmosphere for people working out, and the smell doesn't become unbearable. And I looked at a worst case scenario of the winter. The average temperature was said to be a minus 8.5. And I used the equation that Doug taught us for heating and ventilation, which is Q is equal to 1 over R A times temperature difference, and Q is the amount of heat escaping or entering a room. The heat loss, shown here in negative values, is less than the amount of heat infiltrating from the interior walls. Also, in Edward Pita's book, HVAC Fundamentals, he says that around 2,000 BTUs are given off by a person exercising. So there's more than enough room, there's more than enough thermal energy given off to already heat the rooms, and no additional infrastructure is needed. In addition, in the weight room, as I already showed you, half of the equipment there is meant just for lifting weights or exercising in that manner. So even if we changed over some exercise equipment to generate heat, if you're not using it, you have to rely on the old system anyway. So I've taught you how the room is heated. The next thing you're probably wondering is how is it cooled? And when I ask very short, can somebody who's not from New Brunswick tell me what we're looking at here? Hopewell Rocks, that's right. We're looking at the Bay of Fundy. That's how he said it's cooled. If you remember the pictures I showed you of the inside of the fitness rooms, they both had a large amount of windows. And that's exactly how it's cooled. You open a window. And so with no infrastructure to cool it besides that, it doesn't make sense to invest the money in buying something to cool it further when that's already not needed. Alright, so the last idea for energy use was to sell it to the grid. And this was probably the best idea because it gives us a great apples to apples comparison of one machine to the next. If we're selling to the grid, how long is it going to take to pay it off? And here I've shown quite simply how to calculate the amount of energy it's paying you out. So if you are exercising and generating 400 watts over the course of an hour, you've generated 0.4 kilowatt hours. And in New Brunswick, MB Power charges 9.58 cents per kilowatt hour. And so for your hard work, you would earn less than a nickel. So I want you to bear this number in mind as we look at the machines. And the first up is arguably the most beautiful. This is the Woodway Eco Mill. It's the only treadmill that I found, and there were no retrofits to our treadmills that we could use. It has the price tag of $8,000 US. It is said to generate up to 240 watts, and it has a negative ROI of 0.9978. I think that's bad. Look where we're going from here. Next up is also a new piece of equipment. It's from the Green Micro Gym. They've got a lineup of products designed specifically for this. This is their 6-speed grid-tied bicycle. And in this picture here, you can see that it's folded in half. So it folds up nicely if that's something you need. But it's much cheaper than the other piece of equipment at $1,700 US. It only generates 300 watts and it has a negative ROI of 0.9992. You'll notice that I went into 4 decimal places. That's because if you don't go back that far, they're all -1. So it doesn't lend itself well to comparison. Then I looked at retrofits. The first up is from Convergence Tech. It's $1,364. It's called the Petawatt. I didn't come up with that name myself. I'm sure I'll get accused of that later. And it says that its max output is 400 watts. Now, of course, this is dependent on the person riding it. And you can see in the picture that all it is a stand with a generator with a wheel on it that is driven by friction. It's driven by a road bike that you can convert over for stationary bicycle purposes. And then the box in the picture is to tie it to the grid. Okay. The last retrofit I wanted to show you is also from Convergence Tech, and it's $535. It's called Spin Power. It's the only piece of equipment I looked at that is being specifically designed for use with existing machines. And it said that it could produce an average of 260 watts. And it has a negative ROI of 0.9978, which is the best of any available. But this one is not. I found it on Convergence Tech's website, and I talked with an online help person, and they were able to tell me a little bit about it, but not that it was available. So even our best option, which doesn't exist yet, does not return a positive ROI. The other factor that we have to look at, in addition to the machines themselves, are the people riding the machines. Now, when I started the project, I was worried about the chemical efficiency of people and how much calories they burn riding a bike. And I realized quickly that there were too many variables there, and that frankly they didn't matter, because if you don't have the mechanical output, then you don't get any electrical output. I based my estimates here off of observations and informal interviews with various people who use the gym. There was one time when I was in there, I was not dressed for the occasion, I was probably wearing a blazer and writing in my journal as I was pedaling. And two people came into the room. The first was a lady, and she was stretching after running. And the other was a gentleman who was a bit disappointed in the dumbbells that were in the spin room. And so, in conversation with him, I learned that he wanted more than that. That he was hoping that there would be a proper weight room. And I said, oh yeah, it's just down the hall. And so he left. So the two people that I saw in there, neither of them actually used the bikes. But there is a spin class that happens twice a week, and I've talked to Doug Scott, and he says that they haven't had to turn people away, but they've been full sometimes. And each piece of equipment I've looked at is based on one piece of equipment. You don't get a donut rate for buying a baker's dozen of them. So, with that in mind, I said that 7.5 months a year was a reasonable time to ask people to exercise, or to expect people to exercise. And then optimistically, I said 10 months a year, because technically the college is open that long. If some of these numbers seem low to you, fret not, because my calculations are based around peak output. So it's not reasonable to expect that people would be putting out peak output. So the difference in time would be made up for by the difference in how much they put out an hour. Here is a complete list of the pieces of equipment that I looked at. These are the number of years it would take to pay off some of these pieces of equipment. Even by optimistic guidelines, it would not be paid off in my lifetime, not be paid off in my children's lifetime, it might not even be paid off in my grandchildren's lifetime. Well, maybe if we have developments in longevity. So, in conclusion, the hot water tank was a bit of a bust because it took up too much space. It took too much power, and we already have great existing infrastructure with the boilers. So adding something new is a bit redundant. Another thing that I didn't talk about was power demand. The water heater that I found online was a 3,000 watt water heater. So unless you have 10 people all putting out 300 watts at once, the hotter water heater, you're going to have a cold shower. The HVAC we looked at was also already very efficient. You get a lot of the heating from the other walls, which costs you but doesn't cost you. And it's cooled by opening a window. You don't get any cheaper than that. The machines are, they have a high upfront cost. They don't see a lot of use, not enough to pay them off in a reasonable amount of time at least. And so it leads me to conclude that the college does not stand to gain financially from investing in these machines. And that concludes the information in my report. But I'm not done yet. Because the hard recommendations may be not to invest in the equipment. It might be not to do retrofits that you go out and buy from these companies. And it may not be to change the rooms themselves. But if you have the students build the machines, it's not unreasonable, I don't think. This is, without its hind tires, my mousetrap racer that I had to build for machine design. It was a proud project, one that took more than number crunching to come up with to produce this for my mark. Marks are great, but what if we had an ulterior motive, like competition? We could set up students from different disciplines. What if we could have first years and second years working together on a project like this? I think I've shown from my project that NBCC has great infrastructure, things that don't need change in the works department. But as far as the students go, I think there are some changes to be made. These are the works that I consulted, and I know that this slide says questions, but first I would like to thank again the people that showed up today, the people that helped me with my project. Especially the people in the maintenance department that not only let me have access to the drawings, but also went looking for and digging for the drawings of the building when they couldn't be found. Thank you.
I got a question.
All right, right.
What did the ROI stand for?
That's the return on investment. So to get that, you take the initial cost and you subtract. No, you take what you gain, you subtract the initial cost, and you divide it by the initial cost.
Okay.
Andresa.
Daniel, how did you get this idea?
I got this idea when I was sitting at a rowing machine in a gym in PEI. The display on the machine was blank until I started using it. And I could see quite plainly that it wasn't plugged in. And this was kind of surprising. I was like, so they have all these machines over here, all these treadmills and ellipticals that are plugged into the wall and that take energy, but right now I'm using one that doesn't take energy. I wonder if we could not only have those machines not consuming electricity, but also giving energy back in some way. Dan.
Yes. You talked of putting back the power onto the grid.
Yes.
Do you think it's a feasible option because most of those grids are unable to determine or forecast the energy that will be projected or sold onto the grid? Do you think that's the only feasible option, or is another option you can think of?
No, I don't think it's a feasible option. It doesn't pay back in a reasonable amount of time.
If you were not to put the power back onto the grid, where else do you think you can use that power?
If you weren't looking for financial gain, if you weren't looking to pay back for the machines and you had the students building, I think that a good idea would be to have a way for students to charge their cell phones, because it's something that we all carry. It's an accessible idea, and it's something that we need, sometimes more than others, but especially when you're in the orange zone. Plus, it's like when you're a kid and you're out, you're collecting cans, and you see how much effort it takes to make $1. And you go to the candy shop and you see how easy it is to blow $1, just like that. So it's the same kind of idea. Students get a great educational benefit, which is conducive to the college's mission, without the college having to front that upfront cost. Does that answer your question?
I'm just looking at the grid. Then to start talking of putting power onto the grid, when the grids cannot support the power because we're unable to determine the power that's being injected onto the grid, we'll have to look at alternative options, which is what we mentioned. Good.
All right. I'm not sure I understand the question. Where am I losing you at?
No. You said my problem is, you said we can sell back the power onto the electrical grid. And I'm saying it might not be a good option because if everybody is selling the power onto the grids are unable to determine the power that's coming in. So we have to look for alternative options. And you've said you could ask the students to use them in charging their phone. So it's acceptable.
Okay.
It's a better option than sell it into the grid.
All right, thank you. All right, are there any other questions? All right, well, thank you very much.